In today's video, we are going to derive two new rules concerning circles. The first of which is regarding the length of an arc. Suppose that you have a circle such as this one with a radius that is r, for example, and you have two radii from the center in this form. Then what you have here is an arc. How can we calculate the length of this arc? And let's say that it's going to be called L. It's obviously part of the circumference, but how can we calculate L? First of all, let's have a look at this animation. If I have this circle and this is the radius, I can sweep different lengths of arcs. In this case, this is the length of the arc, and as I rotate further and further, I sweep more of the arc. And the most important thing to notice is that there is a relationship between this angle at the center and the length of the arc. The greater the angle, the greater the arc swept. At this point, when you have a diameter, the length of this arc is a semicircle, and this angle is 360 divided by 2, which is 180. And if you continue going around, the angle becomes reflex, and then you've swept around the entire circumference. So when you rotate by 360 degrees, you've got the entire circumference. Now this implies that there is some kind of relationship, a direct proportion between this angle and this length. So let's imagine this situation. Let's say that this angle is theta, for example, and that this length that subtends theta at the center is L, and obviously the radius is r. We have just shown that there is a direct proportion between the angle and the length. So if this is a full circle, so when the angle that you rotate through is 360 degrees, you go around the entire circumference of the circle, which is 2 pi r. One full circle takes you around the center 360 degrees, one full revolution, and takes you around the circumference, which is 2 pi r. Now if the angle that you go through is simply theta, what's L? Obviously this is ratio and proportion, and you can see by cross multiplication that L is equal to 2 pi r theta divided by 360, which can be looked at in a different light. This is 2 pi r, which is the entire circumference, and you're taking a fraction of this circumference, which is the same as the fraction of the angle to the full angle. So this is another way of looking at it. But if you simplify this expression, it gives you that the length is equal to pi r theta divided by 180, and this is it. Now let's say that we want to find the length of the arc that subtends an angle of 68 at the center of a circle whose radius is 9. This is the situation more or less. We have a circle whose radius is 9 centimeters, and the angle at the center is 68 degrees, and our aim is to calculate this length, the length of the arc. Simply apply the rule. the formula says L is equal to pi r theta divided by 180. Therefore, you have pi times 9 times 68 divided by 180. And this equals, you can use the calculator, so 9 times 68 times pi divided by 180, and that's a fraction of pi, but as a decimal it's 10.7 centimeters to the nearest millimeter. Now let's calculate the area of a sector. Let's imagine that we have a circle in this form and we want to calculate this area. We can do the same exercise that we have done before. Now, instead of focusing on the length of the arc, focus on the area of the sector. The bigger the angle, the bigger the area of the sector. Now, it's obvious that you have a right angle here and that this area is a quarter of the circle. Here you have 180 degrees, which is half of 360 degrees, and you have half of the circle. And if you continue, the bigger the angle, the bigger the area of the sector. So we can conclude the same idea. But let's look at this logically. This slice of pizza is obviously 1/8 of the pizza, assuming that the angles that these slices are identical. If it's 1/8 of the area of the pizza, look at this angle. It's 1/8 of the central angle, which is 360 degrees, the full revolution. Therefore, if we are to derive a rule, the full revolution of 360 degrees gives us an area of pi r squared. A theta at the center gives us a certain area of the sector. So it can be seen that the area of the sector is equal to pi r squared theta divided by 360, which in turn, in much the same way, can be thought of as the area of the circle, which is pi r squared, times a fraction equal to the fraction of this angle compared to the full revolution. So our rule is simply pi r squared theta divided by 360, and that gives you the area of the sector. Theta and area, so the area is equal to pi r squared theta divided by 360. And to be sure, this is the area of the sector, not the area of the circle. So, if the radius of a pizza is 25 centimeters and a slice is taken such that its central angle is 38, find the area of the top of the pizza. This situation can be simplified into this diagram, and if the radius is 25 centimeters and this angle is 38 degrees, then we're looking for the area of the sector. Simply A is equal to pi r squared times theta over 360, and substituting the values gives us pi times 25 squared times 38 over 360, and this equals pi times 25 squared times 38 divided by 360, and this is 207.26. square centimeters. And I've taken this value to a higher degree of accuracy because I know there is a section B of the question. It says that if the thickness of the pizza is 2 centimeters, so this is the thickness of the pizza, we want to find the volume of the slice. So the thing is to identify the slice as a prism where the cross-sectional area is constant and the cross-section is the sector. So the volume of a prism is, as you remember, the area of the cross-section times the height. In this case, we have already calculated the area of the cross-section, which is the area of the top of the pizza, as 207.26 times the height, which is 2, and this gives us 414.5 to 1 decimal place cube centimeters.